Hello everyone and welcome back to my channel. Today we are going to talk about latent diffusion models, which are a cornerstone of all modern text to image models you see today, whether it is Stable Diffusion, Flux, or similar systems. The key idea here comes from the high resolution images. You can check out the original paper here. First, let's understand what latent diffusion is and why we need it, and the limitations of basic diffusion models. In a standard diffusion model like this, we start with an image. We add noise gradually to create a noisier version. We pass it to diffusion model to denoise it and generate the output. So here, this is the noisy input. We pass it to the model, get the denoised input. The problem? GPU uses and computation scale drastically with image resolution. For example, you can see here a 64 cross 64 image. Here is the x-axis is the resolution of the image and y-axis is how much GPU is needed to pass through the same diffusion model or the same UNet. The UNet parameter is not changing here. So a 64 cross 64 resolution takes around 300 MB of GPU. However, increasing it to 512 cross 512, the GPU memory jumps almost 10 times, even though the model parameters haven't changed. This is because the computation depends on the number of pixels, not the model size. If you increase model size for higher resolution, it can easily become unmanageable. There is also another thing that when you train a diffusion model, the higher the resolution of your image is, the longer it takes for the diffusion model to converge. So that's why this is the main problem when you try to generate high resolution image using diffusion. So how do we generate high resolution images without exploding computational cost? The key idea is do not apply diffusion directly on the full resolution image. Instead, encode the image into a latent space using variational autoencoder. Apply diffusion in the smaller latent space where redundant information is compressed. And after you finish with the diffusion process, then decode using the VAE to the original image resolution. You can look at this paper for more details. So how this diffusion works? We take a high resolution image, let's say a RGB image with 512 cross 512, pass it through the encoder of the VAE to get a latent vector, which is of shape 4 cross 64 cross 64. And we do the diffusion on this latent space and then decode the latent vector back to the original resolution. This is a simple diagram that shows exactly the same in a simplified manner. This is the encoding. We do the diffusion here. This can be forward diffusion or reverse diffusion. And then after the diffusion is finished, we use the decoder, this decoder, to get back the original image resolution. Of course, we can add conditioning such as timestamp conditioning, class conditioning, or text conditioning that we're going to see in the next video. This is the core structure of a latent diffusion model. So first we import all the necessary libraries. Then we create a UNet model. And this UNet model has around 17 billion parameter. Then I generated a different set of random tensors, one having resolution 64, 128, 256, and 512, and pass it through this UNet to check the peak memory utilization. And we see that it rises very steeply with image as we increase the image resolution. Next, we are going to import the variational autoencoder. This variational autoencoder is trained on general images. It can encode and decode any image very effectively. Then I load the dataset. It is the dataset of celebrity faces, which looks something like this. And this is another image. Let's say do 67. So yeah, we got different. This is basically images of celebrities. Then we apply transformation such as resizing, converting into pytorch tensor, and then normalizing. I took first 5 images, and then I do the transformation on top 5 images and stack them together to create a tensor. So now my image tensor is of shape 5, which is the number of images. 3 is the RGB channel, and 512 cross 512. Now we'll encode these images using the VAE. So for that, it's very simple. We do VAE.encode, we pass the tensor, and then do dot latent distribution dot sample. So this gives us the latent. This latent is of shape, so it is of shape batch size, which is 5, 4 cross 64. We can do this by So one another thing I want to show here is the range. That originally the images, these images that we have a range between -1 to 1. But after we pass it through the VA, they become very high. They come across a very high range from -57 to 40. This is not desirable as this latent is gonna go through the diffusion or into the UNet. So what we do is we scale it by some factor. The scaling factor is available inside the VA. So what happens after that is the range is now less. And before which was -57, now it's -10 to 7, which is more manageable. And if we see the image from the first latent, we see, okay, this is how it looks. It's a 64 cross 64 and 4 channel. I just take the mean across the 4 channel just to show them more easily. Now comes the decoding part. The decoding is also very simple. We take the latent and divide it by scaling factor. Here we were multiplying by scaling factor. Now we are dividing by scaling factor. Then we do the va.decode to decode it back to the original. The original and constructed are barely, it's very difficult to see any difference. With this, we can see that we can easily do diffusion on this latent space, and we can, using the VA, we can take it from the original resolution to this smaller resolution whenever we want. To verify, we create a UNet model. Now the UNet model parameter are a little different because our latent image is of shape 64 with 4 channel and output 4 channel. We change that, and this is our UNet model. And if we do the peak utilization, we see that it only takes 100 MB, which before used to take around 1000 MB. Hence, this allows us to generate high resolution images with minimal computation while still performing full diffusion steps. In the next video, we'll explore text conditioned latent diffusion model, which form the backbone of stable diffusion. We'll see how to do inference, understand key parameter, and explore various components using the diffusers library. If you are enjoying this diffusion series, subscribe to the channel and stay tuned. I'll see you in the next video.